very, quickly. That yeah. So StatFin webinar series we have started. So this is the first event. So the idea is to have such webinar series twice every semester, or you can think the 4 times a year. And every webinar would contain 2 talks. So that is the plan. So it would continue every year. Okay. So this is one, additional sequence of events what StatFin is organizing, other than their annual or workshop and conference, which for past few years are being held during the summer. So yeah, welcome everyone. It is a really, pleasure for us to have all of you here. This is quite in the evening, Friday evening, like movie time kind of things. But thank you for your support. And I really hope that this webinar would become very popular, and it would be very useful for the students and academicians, or maybe some practitioners. Okay. So by saying so, let me request Professor Ramanathan to start his presentation. So he is going to give a research seminar now. Here the talks would be a little less than 1 hour, like 50 minutes. And there will be 5 minutes short break before the second talk starts. Okay. So thank you very much for your patience. Okay. Yeah.
Thank you, Anindya. Thank you for inviting me to give this seminar as a StatFin webinar series. Again, overuse of things can create problems. So my laptop got crashed and I lost the presentation. But then I managed to pick up an earlier one. So, and then I am unable to actually format it because of the tech problems. But anyway, most of the things are there. So there's not much damage done. So that's why you see a bit old. There is a slight extra line on the title also. Few things extra, but doesn't matter. Let's forget that first slide. So I'm going to talk on a recent development on model selection, what is called focus information criterion. And so all of you may be knowing, so this is basically I am talking from the perspective of students. So there are several things will be explained a little more detail as opposed to a research seminar. But of course, definitely there are a lot of research component. Problem. Do you see a small window in between? It's not there, no? No. Okay. Now it is clear. Okay. So I will be taking you through the model selection, some existing criteria, and then I will introduce the need for this a new criteria, which of course this was introduced by Klasken and Hioth sometime in 2003, and then mostly for a couple of years it was used for independent data, and then when you have stochastic processes or models based on the stochastic sequence, how this can be made use of. So that is where we try to contribute a little bit. And yeah, so and then I'll share you some of the recent developments or recent work that we have been doing. So models, basically all of you know this particular anecdote that all models are wrong, but some are useful. In fact, I would say this focus information criteria is really sort of justifying that to a great extent. And those who are involved in this model selection, they all know that there is a game of bias and variance trade-off, that you try to fit a model which gives a very good fit, but then at the cost of something. And if you want to reduce that, then it is at the cost of something. I mean, basically, overfitting, reduce the bias, variance increases, reduce the variance, bias increases, which all of us know. So we try to compromise this by saying that, okay, let's have some parsimonious model where, you have less number of parameters. That's what we accept. Now, two important, this in this context, actually, I'm getting a window in between and it comes very frequently. Okay, now it has gone. The purpose of the model is not to fit not just to fit the data, but to sharpen the question. This is what Samuel Carlin has said. And similarly, nowadays, every statistician is turning to be a data scientist slowly. So, the Leo Brayman, he said that sort of scientific questions, sort scientific questions into respectively those of prediction and classification on one hand, and those of deeper learning about models on the other hand. So basically, we are trying to have use of model, basically. So we are into that. So I don't want to compare any of this discussion to the without model that what we have been doing. So it is clearly the typical old the likelihood based or maybe robust versions of that based model selection criteria. So that is what we are in. Now we will be talking about a little bit of focus, and then sometimes there are conflicting recommendations of the model, because one criteria will give you another a model and another criteria will give you another model. So, and as a solution, it was suggested that model averaging was suggested. In this today's talk, I'm not getting into the model averaging. So statistical model selection is an important and integral and inevitable element of any data analysis. And perhaps those who have read Klaskin and Heor's book, at least the first chapter on model selection and model averaging, might have seen this example, which I like very much, that the authorship detection, the great controversy of this particular novel, And Quiet Flows the Dawn, written by Mikhail Sholokov. And then there was an allegation sometimes around 73, 74, saying that this was lifted from Fyodor Kryukov, who was also a great novelist from the Russian literature. And then it was supported by, whenever there is a controversy, if somebody come and support, especially that person also is having a high standing. So Alexander Solzhenitsyn, who later got Nobel Prize, he came and supported that allegation, and then this has become a big issue. So there were several type of investigation, and one of them statistical investigation, authorship detection, and Neil Heort was involved in that, and he had written this example in that book as well as in a small note on that, trying to see the number of words in a sentence and then try to construct a corpora of words and then see that how truncated Poisson can be used for this, because you need at least one word to have a sentence. So what kind of distribution, I mean, basically truncated Poisson type the count data models. Different models were tried, and then trying to establish that there is, I mean, the controversy is actually not valid, or the three different corpora that he has collected from Kryukov, as well as Quiet Flows the Dawn, as well as Sholokov's other work. The match is more with Sholokov's other work. So that's how justified the whole, I mean, like the authorship sort of justified, because it was Nobel, Prize controversy. So one Nobel Prizes are generally for the original contribution. So when there is a lifting, naturally it requires different types of investigation. So this point was discussed very heavily, and then he motivated there with the model selection problem. Very good for students to read. If you are not aware of that book, that's by Klaskin and Heor, Model Selection and Model Averaging. Now, of course, in finance, there are a lot of, symmetric versus asymmetric models, normal versus, asymmetric, normal, leptocratic. So there are various occasions in which heavy tail distributions or asymmetric distributions are useful in the context of financial returns or financial variables. So model selection is definitely an important activity over there. Actually, there is a paper by Lin and Shrestha sometime in 2005 where they were trying to fit a error correction model for the hedge, like the spot and future price, and then try to find what is the order of this error correction by using the focus information criteria as well as other information criteria and making a comparison, and then finding that FIC is doing a reasonably good job over there. So there are a lot of applications. So in regression models, one want to select appropriate subset of predictors, which is one of the important aspects. In time series model, the order, we need to detect the order of dependence. So AR1, AR2, AR3, etc. So time series model, the question is that what is the kind of error that you have? That is where the model selection is also important in terms of Gaussian, non-Gaussian. The last one which I'm going to discuss, I will be discussing little more detail, so I'm not getting into that right now. So the existing there are several information criteria. I am not going to discuss all of them. One can look into the standard books on this. So there you will get these ideas. So I will just narrate 3 of them here, which are heavily in use. And one is AIC, which is used by even not necessary even statisticians. I mean, like several applied people, when they want to fix a model, they use the AIC, which was basically introduced in the context of signal processing. And this is regarded as one of the important breakthroughs in statistics in the 20th century. So the basic idea there is you penalize the likelihood criterion. So you try to have approximate unbiased estimate of the KL distance, the KL distance, which I have written here. KLGF is that finally leads to something like this, where M stands for the. Am I audible? Because I get a message that internet is unstable.
Here, your audio is fluctuating a little bit. Sometimes okay. Your audio is going down, so I don't know why.
Yeah, that is actually this. I'm using the university network because I was in the office. So I don't know, maybe that is the reason, but I can't do anything about that.
Anyways, how are you going to take questions? Should people ask questions in between, or they should write in the chat? What would be more comfortable?
Everything is fine. Everything is fine with me. So okay. I think at the end that would be better, because in that case I will be talking at least without a break, so that then we can take them at the end.
Okay, great. So we will have questions at the end.
Yeah. Okay. So this is the AIC that everyone knows that finally the derivation leads to this type of a formula, where the derivations are available in standard textbook like Bunham and Anderson and Klaskin and Hjort. And there is a latest book by Konishi and Kitagawa. Of course, it is available in several other books as well. I just pointed out because it's so common, especially when a time series course is taught. We used to have these derivations in the MSc level class. So basically, if you look at this is popular among the model selectors and applied statisticians, and it has a tendency to overfit. That's one of the problem regarding this particular criteria. And another popular criteria is in the time series context. In the time series context is make a correction in the penalty, and that is what AIC corrected. And this is suggested by Hurwitz and Say. Of course, this is basically for regression type of models, regression or time series type of models. And the difference that you can see here in the penalty is, this is the penalty. So it will have slightly more extreme penalty as compared to the AIC, which we have. By the way, all these criteria, this first term is more or less same, most of the criteria. So that is about the -2 of the log likelihood. Now, this is not that popular, whereas BIC is very popular, where you have, you might have seen most of the applied statisticians, especially when you are dealing with the dependent data, you may be preferring BIC as compared to AIC, knowingly or unknowingly. But the reason is that this was proved to be a consistent model selection. BIC is proved to be a consistent model selection. In fact, there is a book by Ghosh and Samantha. So a lot of discussions are available for students. I would recommend to read this book on Ghosh and Samantha. So this again, as I told you, the proof is available in this. So here the difference is that you try to have, instead of the likelihood, you try to consider the posterior probability. And ultimately, in the formula of the BIC, you don't see any Bayesian flavor over there, even though you start with all these things. So that's how the formula is made very user-friendly finally, where the first term is just a -2 of likelihood, and the second term you have a penalty, which is going to depend. I'm sorry, there is some, depending on this log n dimension of M. Now, the question here is, so there are proofs or theorems where it says that BIC is a consistent order selection criterion. What is this consistency means? So a model selection method is consistent if with probability tending to 1. As the sample size tends to infinity, the selection method is able to select the true model from the candidate models. So if you have, that is what the consistency means. This doesn't mean that you have to have the candidate model also in the collection, but if it is, because this is a limiting property, so there you can also have, it is outside, but the true model need not be amongst the candidate model. In such a case, we assume that there is a candidate model that is, something is disturbing me here. It's closest to the KL distance to the true model, and the model selection method picks that such closest model with probability tending to 1. So this is what the theoretical, the derivation of consistency. You can also have a property what is called as efficiency, where you try to see that how much loss that you are going to have by selecting a particular model, and then you try to minimize that. So that leads to the what is called as efficient model selection. So there are theorems and discussions on this, which are available in standard textbooks, efficient model selection as well as consistent model selection. Now, the question here is, in all these above examples, the model are to be chosen with certain purpose, a context in mind, because there is some reason that we go for the model selection. So, for example, in the asymmetric Laplace example, the context is symmetry as well as peakedness, coefficient of skewness and kurtosis. I'm talking about general financial application. While selecting AR model, it could be the order of dependence. While talking about a general Markov chain, the transition density or conditional mean, conditional median could be of interest. So you have something in your mind that this is what I want to work on, even though then you go and select a model which is sort of, which doesn't take this into consideration, whereas it go for the whole of the model. Because you go for the complete likelihood and then try to find a model which can be used. Now, the question is that, can we focus on this, what you want to do, and then select a model? So this is what one question. So these functions are generally called as the focus functions. So the context, the focus always underlies any model selection routines. So the data analyst hence should identify that in terms of suitable functions prior to the model selection. So this is what this group of people recommend or suggest, that there is no need to go for a universal best model, but you need to know what is best for you and what you are going to do, and then justify it based on that. So moreover, any model selection method should take into consideration such user-defined focus function, the context of models. So the question here is, does AIC, BIC, or some of the existing ICs, does it do this? Or are they worried about the focus? So the answer is no. They are not worried about the focus. So they are simply the maxima of the log likelihood with a penalty. Because penalty is basically to adjust the bias or overfitting. So hence they provide a unique model as the best model without taking into consideration such particular functional forms of interest. So that is what. So now the two researchers, Gerda Klaskin and Neil Heort, in 2003 JASA paper, they came up with an idea that the model selector should focus on the parameter singled out of interest. So the best model should depend on the parameter under focus. And then what they try to do is that minimize the MSC of the estimator of the parameter being focused to select a model. So naturally, when there is a focus parameter, it depends on, different, for a parameter, naturally there is an estimator. So my estimator need not be the same as another person's estimator. So naturally there will be some kind of subjectivity is going to arise. So what is suggested is that actually that subjectivity, this subjectivity they did not address at that point of time, mostly because they said that these are likelihood based procedures. So and in asymptotic, what happened that if your estimator has certain properties, this subjectivity actually is not going to create much of a problem in the model selection context. I'm not talking about directly how this particular estimator is, but of course the estimator is coming to picture because we are talking about the MSC of that estimator. So I'll talk about that a little later. So the large sample theory of the estimators is used to develop the FIC. So since the bias always dominates when the true model is at fixed distance from the smallest model, so we study the model selection properties in a misspecification setting. So Anindya, I am audible, right?
Yes, I can hear you.
Yeah, you are audible. That's fine.
Okay. Now I just want to check. So that's all. So let me now explain this the context a little bit. The focus model selection. So here there is a smallest model and there is a biggest or narrow and wide model. So the smallest one is like you have, for example, if you are considering this particular setup where you can now see that there is a theta naught and I have put gamma naught plus delta by root n. And if for example, if this is totally is not present, that I don't select any of these things. So this is, of course, it's for the realistic sense, like what essentially the selection we are actually doing it in this context only on gamma naught. But this will be there in all the model that we are considering. Theta part is there in all the model that we are considering. Well, if you don't have that theta part, then you will be doing the model selection with this. Okay. So to study the perturbations of Fy theta for this around this gamma equal to gamma naught, where we assume that this is a q-dimensional thing. So there is a value gamma equal to gamma naught, the wide model that leads to the narrow one. And then you have this gamma 1, gamma 2, gamma q. These are the possible values. Possible in the case of, the wide one. And we would like to select a model in this context. So the focus parameter is based on, I have actually, there is a focus that I will be concentrating, and that there's some problem with the presentation. All the time I'm getting some disturbance over here. So the focus parameter is mu theta gamma, a parameter of direct interest, which is based on the context. Right now, I'm not saying what is that focus parameter. I will make some assumptions, and then for this parameter, we claim that with certain assumption that you have a clean likelihood theory available. Now, if not likelihood, if at all, I mean, I want to make it robust. In fact, in most of our discussion, we deviated from the likelihood. We deviate to quasi-maximum likelihood. We deviate to robust, functions, different types of robust estimators. But basically, there is a focus parameter. Okay, so models are considered with all the components of theta, but not sure about that of gamma, and that's where some or no, none of them. So the true, this is the mu theta naught, gamma naught plus delta by root n. That's what the true model. So there are 2 raised to the 2 to the power of q model subset estimators to consider, ranging the narrow model from S equal to 1 to etc. So S stands for the selection set. Okay. So what you do for the selected S, you consider this estimator and consider the asymptotic distribution of this quantity. So this is where we need to establish some kind of local asymptotic normality. As I told you, we are considering nested models. So we will have to have a, this is completely based on proving. So I may have to make the appropriate assumption that the local asymptotic normality theorems can be established for this. So that is what the maths part of it. So the above step will give the MSE of the limiting distribution of this for any S. So estimate the risk quantity for each S under consideration, and that actually yield the model choice. Whichever is having lowest MSE, you'll select that. So the best model is the model for the estimation of the focus parameter mu is the model for which the MSE of the limiting distribution is the smallest. So FIC is based on the estimator of the MSE. So the model with the lowest value of MSE, FIC is selected. Now, there are other variations which we are not discussing today because you may, why MSE, why something else? So I am not discussing, but there are a lot of discussions on this. One can look into the absolute error and related model, changes in that. So I'll just illustrate something in the context of a simple regression. Say, for example, I have a simple regression here where mu is included in our model. So you have something like a theta, mu plays the role of theta, and my selection is in the beta. So this is what the S which we represent. So I'll represent my beta m in this manner, depending on the selection matrix. So this is a selection matrix. SM is a selection matrix. And then this is the estimator of the full model. And so the focus parameter is, suppose the focus parameter is this G beta, some function of beta. In the linear regression, that is what is the case. And I will use this delta method to actually get the corresponding the MSE. So with some assumptions and asymptotic, normality, we will be able to, of course, I have to make appropriate assumptions to have the asymptotic normality. That is an inevitable part of this entire theory. You need them. So I can get the, so this is like bias square, so the variance. So this is what you get the corresponding, the FIC expression, the MSE expression. So MSE choice of M is the value of that which minimizes this, is called the focus information. Well, this was discussed by Klasken in the first paper. And then these people started working on this, extending this idea to various different contexts. So this is not an exclusive list, but I just point out few things because especially my interest is in the dependent data case. So a number of applications in regression variable selection that include generalized regression, logistic regression, auto-regression models, linear hazard regression models, and this I already mentioned, an application in the context of co-integration, error correction models, etc. So there are several applications one can see. And this was also extended in the context of dependent data, where you have this paper 2007, where they considered into extend this to a this paper appeared in Australian Journal of Statistics, where the same authors tried to work on, that was the first paper where the dependent data is considered. So they worked on AR models, and their focus parameter is the prediction. So what they consider is the conditional expectation, which involves the past values. But once you condition on them, they are known. So basically, the parameter is going to appear in the predicted. So they try to have the FIC theory developed for this particular case, and that appeared in Australian New Zealand Journal. So where we try to see that whether because when you get into from AR to more complex time series model, the asymptotic theory is a bit more involved. So perhaps that could be the reason that they were unable to, or they might thought of doing it later. So somehow we got a chance to do that exercise. So what we did was that there is a neat asymptotic theory available in the ARMA context. So we use that and then try to develop the theory for the FIC. And so of course, so this is what the details of the Klaskin's paper, which you can see here. The focus parameter is H step ahead predictant, and then the plugin method is used that for the P observation and the earlier predicted values. The method also depends on the estimates of the model parameters, because the focus, the focus you can get the parameters, because once you identify the focus parameter, and when you start estimating, naturally this will come. So this is what then what we did was we tried to extend this to sort of ARMA models. So this is what in that particular paper published. Of course, ARMA has again, Brockle and Davis gives you a kind of neat asymptotic theory. So we made use of this asymptotic theory, and then developed the focus information criteria in the context of ARMA model, and established that it is working almost in par with, or sometimes even better compared to the AIC, BIC, etc. Of course, we don't have a universal kind of a thing, betterment or anything that I am claiming, because first of all, BIC is a consistent model selection. FIC is not a consistent model selection. So that way, it's not directly comparable in that way. But there are some theorems proved by Klaskin and Heor under certain conditions that you can see that the FIC is very close to the AIC, which is proved in their book. So those students who are interested, they can have a look at that with a couple of conditions. Okay, so here what happened then we thought that, okay, is it possible to extend from here to generalized linear models? Because there are a lot of applications of generalized linear model in the context of biostatistics applications. So that's where this particular thing has been extended. So here, now once it comes to generalized linear models, with a dependent setup, and that's where we started. And so, of course, those who are working in this area, they know that GLM as a time series was introduced by Ziegler and Quackish in 1988, and then Lee in 1994. These are the fundamental works. And then there they basically try to estimate the given parameters based on the theory of estimating function, generalized estimating functions, etc. Now, what we did, okay, I think I can just consider this, okay. So I'll get into this particular setup because this is where we derived the FIC in the context of logistic type of family first time, and then that has now appeared in the special issue of Journal of Statistical Theory and Practice 2021. So this is here what we did was that, so the setup is like you have a Markov process, and then you have this, and then this is the canonical link function. And this is, so you have the dispersion parameter. So we assumed that you have, this is the function that we are considering. So you have some regressors as well as you have some, this past values of y's. So in the model, so the selection is, you can have the selection with respect to both of them is possible. Because what essentially needed that, depending on the focus parameter, you need to have a clear local asymptotic normality theory. Once you have that, you can actually pick those variants or the MSC components from that from there, and then get the FIC expression. So this is the general trick or general kind of methodology that follows in most of these discussions. Well, so here you have the, you have, so the narrow model is this as far as selection of this is concerned. And the wide model, if I assume that all these things are there, you can also have a selection in that particular case as well. So this is the P+2 parameters in the narrow model. And then, so if you are selecting this, then you are putting your gamma with all these parameters. So naturally the selection is here. So this is additional Q minus P plus K parameters in the wide model subject to selection. So the wide model reduces to the narrow model when you have this, this is equal to 0 Q minus P minus K. So you don't have, so basically if you are putting all these into selection, the narrow model is just with the intercept. If you are fixing some of them, just consider the remaining into this particular. So that's how. So what we require, so make some kind of, so this is the setup that everyone knows, that you are in the exponential family, and then we derive the FIC using the asymptotically efficient estimator beta hat. So here, as I told you, that because I don't have, I'm not making a particular kind of an assumption. So this is not necessary an MLE. We can have the QMLE also possible. It can be discretized one-step estimator QMLE obtained numerically. In fact, that these details are available in the book by Van der Waard. So you don't have to have, I mean, like the MLE, because if once you have the asymptotic theory available, this we can extend into any of those things. Okay. So here I'm just writing this, the mathematics of that. So you have the asymptotic, the wide model, the corresponding, the sample conditional precision information matrix. And then you see, this is something very crucial where you can make this partition with respect to the partition of the parameters. And that actually work the crucial point in this. And then it is like, finding your LAN theory is applicable over here, and that should be doing the whole job. So that's what I told in the beginning. We are still in the traditional model selection setup, but only thing is that it is based on some focus parameter rather than a global kind of a good model that you are selecting just based on the likelihood. Okay, so this is, you have this measurable focus function, which is like here you can select this. Now, when you are into logistic type of setup, maybe, you may be interested in various different odds ratio or different types of parametric functions are of interest. Unlike in the traditional IID setup, focus can be a measurable function of the past data in the time-dependent setup that all of you know. I already mentioned that in the case of time-dependent or time series data, conditional expectation can be a quantity of interest. So the rest of the calculations in terms of, involves, it's the usual asymptotic theory, which I'm not getting into the detail. As I told you already, that it is all based on getting this particular one. So this is where you have, so I'm skipping all those details. And because you have a dependent setup, central limit theorems are not easily available at your disposal. So you need to make appropriate assumptions So this is what all these assumptions are. And, when you are in a regression context, naturally, you have to make assumptions on, to have a central limit theorem, you have to make assumptions on regressors as well. So all those things are applicable over here. And with that, you apply this central limit theorem and then prove this, this particular result where you have, actually there is some disturbance coming. Yeah. So you get something like this, this is what, and then I will able to pick up this particular one. And this whole thing involve, the land theory. So I'm skipping all of them. And finally, I'll get into the FIC expression. So you get this FIC expression into that. Those jargons are mostly standard. Only thing is that it is not that straightforward. But I think once you are into this setup, you can, with appropriate conditions or assumptions, you can get those things. And then the FIC expression follows. So as I told you, the FIC expressions are conditional MSE of the estimated focus function. Now, FIC submodels can be derived by augmenting the additional parameters into submodels to the gamma vector and repeat the above procedure with the new gamma. So the thing is that until this work, mostly the FIC has been discussed in the individual basis for classical statistical models like IID data, Gaussian, and then logistic regression models, and Gaussian AR or ARMA. So this is the first time that now this has been extended to a GLM setup in the dependent case. And then we started with the logistic kind of setup. And then we could actually relax that assumption and then go into the general logistic regression setup, which is called as logistic ARMA or generalized ARMA models. So that is what the subsequent extension, which has appeared recently in again Australian New Zealand Journal of Statistics. So so here, if you consider Q equal to 0, I mean, this with the model with no regressors, that's model for the IID data, and this was considered. So I want to claim that this basically some of the earlier work you unify, because if you have this Q equal to 0, like you don't have that dependent part, then you are back to the logistic regression. And if you say this identity link function, you are in the linear regression with dependent response.
The speaker is, I think, logged out. So I've contacted.
What happened? We have lost TVR.
Yeah, we lost the speaker. Yeah, but let me see. I think by now he has also understood.
Maybe you can pause the recording on in there.
Sure.
Can somebody call him, Anindya, Rituparna?
Yeah. Hello. Okay. Yeah, the speaker is trying to connect.
I'm sorry, there is some internet issues.
Okay. Yeah, now we can hear you.
We can hear you now. Are you able to use the video or share the screen?
I'll just try to use the slides. Is it visible now?
Yes.
Yes.
Okay. Sorry. Okay. So I think I don't want to use the video for the time being, but the slides are visible, right?
Yeah, the slides are visible. So maybe you
Okay.
can just switch the video off.
Yeah. Yeah, because the strength is low. That is why.
Right. Anindya, you may start the recording again.
Okay, I think this is the point where so this is the point where I was. So many of the earlier work, because once we generalize into GLM ARMA model, earlier thing turns out to be special cases of that. And this now actually I wanted to, we had applied this to a study to see that how this works in context of a data. So this is a very famous data, Indonesian child data, like Indonesian children health study data, which has, more than about 3,000 children were, examined for 2 years through 6 quarterly visits to determine the presence of respiratory diseases. And these are some of the variables or predictors or regressors which are there. So why is the dependent and response respiratory infection healthy and infected? So this is like a panel. Continuously you observe. So you have this age of children, presence of absence of this particular seropsalmia, which is kind of vitamin A kind of deficiency kind of thing. And then you have gender, height, stunt growth, etc. So about a random sample of 275 children in our library, you can see that. Hello. Yeah. So we applied this, and then some of the earlier work which used this data are here. You can see them. Some of the earlier work which used this data. However, most of them were using like AIC, BIC kind of thing. So we thought that we can actually try and do FIC in this context. And then this is the canonical, the logic is given by this. So the response is binary and measured by 6 quarterly visit. There's a logistic regression model with Markovian component of order 5 and 5 covariates. So you can see this is what the betas. Of course, there is a kind of multiplicative effect here, and this is what the model that we have. So there, of course, we have to be careful, because in this context you are to make sure that three of the conditions, so the assumptions of stationarity of response process and time variance, invariance of coefficients are seen to be true. Then we tried to see, we did separated this for the boys and the girls, and then try to see kind of what kind of models. So the covariates combination is indicate a the predictor that is included. This is omitted. So this is model selection and validation for the candidate models. And for FIC, the focus function is, we have considered actually two of them, the logs odds ratio. The other natural choice of focus function is the probability of infection. And these are pretty related. So you can also see that FIC expression, if you turned out to be those two foci are positive scalar multiples of each other. So that actually, the choice of models remain unaffected by the choice of a focus function between these two. I'm not saying that is not in general, between these two. So the log odds ratio being a linear parametric function simplify the FIC computation substantially in this particular case. Well, if you go for a different focus function, naturally you need to develop the corresponding asymptotics, and then naturally the model, the FIC expression also get more and more complex. But it all depends on what is the focus, because the contextual model selection is that we are talking about. So in the context, what is your context? So that's where these functions help. So there are, now this, whatever that we have the result, I've given all the details in the interest of the time. What I'm just skipping them, a few of them, but we have more or less similar kind of a result. 3 out of 5 models in girl stratum and 4 out of 5 models in boy stratums are common between AIC and FIC. And all these information criteria show that the age is not seen to be more dominating. So that you can see, I've given with different colors over here. So this is in the case of boys, this is in the case of girls. So you see the corresponding AIC and this FIC expressions. So you can see that more or less all the 3 IC shows the age seems to be more or less dominating in the case of respiratory infection in the girls. Height and stunning of growth have relatively more prominent impact on the respiratory infection in boys. So these are some of the outcome of this data analysis exercise. What we have is, we don't have a altogether fantastic model selection criteria which is now totally supersede AIC BIC. We are not claiming that, but the idea is that you have a contextual model selection is being developed, and that helps in many contexts because you don't have to go for a universal best model, and sometimes depending on the parameter, focus parameter, things would be much more easy in this particular case. And what we could also demonstrate that the model chosen with this particular criteria, and if you again look back the MSC of the parameter, the estimates, we can see that naturally that also on the better side that you have smaller MSC. That also we found. And then we also found that the model select chosen, the chosen with FIC are also found to be consistent with those significant variables identified by the p-values of the wall test. So this most of these this particular example, in fact, in the Journal of Statistical Theory and Practice paper, we have given one more example on cancer data, Wisconsin cancer data, but similar kind of a setup. But of course, the dependency structure is slightly different over there. But again, a logistic example, whereas here I've given a different example. In the GLM context, we have actually analyzed the Australian rainfall, Melbourne data, which is also very popular, to generalized to select a generalized ARMA model using these FIC ideas. So these are some of the applications of this. Now, I think I skip some of these analysis where because there is nothing that what we have extraordinary findings, but what we found that model selected by FIC and AIC exhibits smaller proportion of incorrect classification and higher AUC area under the curve than the BIC models. The FIC performs better than the BIC in this particular case, and is in par with AIC case. So the concluding remark is that the proposed setup, the time series GLM, brings the model selection for a classical parametric model under one roof, and data analysis reveals that FIC better than BIC in some situations and at least as good as AIC. These are some more specific to these examples. So the crux of the FIC is identifying the parameters in wide and narrow models and partitioning the asymptotic covariance matrix of parameter estimators accordingly. And to have that covariance matrix, you require a LAN theory. So this is what basically, now LAN in the sense that one may think that this is only applicable to maximum likelihood, nothing like that. This is applicable to in the robust setup also. In fact, we have another paper which we extended this thing to L2 differentiable quadratic differentiable functions. And for example, we don't have standard assumptions in the context of Laplace distribution. So whereas QMD is available, quadratic mean differentiability is available, so that we can develop the model selection criteria using FIC, because asymptotic theory is available. So this is what a paper which is published a little earlier, 2020, on stochastic process and inferences. Well, that's all about, so this is the stochastic process. Have extended generalized notions of FIC to general stationary ergodic stochastic models. So I think I'm almost done. So we can take some questions. This is the book for students. It will be helpful. So thank you for your attention. So I'll check whether in the chat box, that chat box have gone now.
No, I mean, the chat box is here, but no, okay. I don't find any question here.
Okay.
The YouTube thing also, I find no question here also. Now, participants may ask questions.
Hello, sir. Am I audible?
Yeah, sure.
So, my name is Dr. Arindam Kundu, Assistant Professor at Department of Mathematics, Adams University.
Okay.
First of all, thank you, sir, for your nice lecture. Sir, I want to know that, can I use this model selection criteria, that means FIC, for nonlinear regression model?
Yeah, you have, as long as your functions, you have differentiability is to be assumed, and then you have a clean asymptotics available. So whatever stop, the asymptotics, then you may have to have stronger assumptions. But otherwise, usually we have the asymptotics available for the focus parameter. So depending on the focus parameter, if we can develop a local asymptotic normality theory for the estimator under consideration. So it could be whatever estimator. Generally, least square or non-linear approximations, approximate least square, or I mean, like whatever. I mean, even robust estimators can be useful. So if you have the asymptotic theory, perfect. Definitely, the focus the information criteria formula can be developed. And then once you have the formula, then you can plug in those estimators over for the parameters over there, and then the FIC can be used. But I am not claiming that this is going to be a superhero compared to the BIC and AIC. There are situations where it works better. That all depends on what is you are trying to do, because what is your focus?
Yes, sir. Yes, sir. Yes, sir. Actually, sir, I have used AIC, but then, sir, I just want to check that if I mean, instead of AIC, if I use FIC, so I mean, how my result will be changed actually. So
that you have to use it and see. Maybe you have to use, because it is already applied in generalized linear model regression context. There is a paper, in the original paper itself, they have tried to apply, but not all focus, I mean, the parameters are covered. I think in the first paper only, I think they looked at the odds ratio as the parameter, but subsequently, I mean, any differentiable parametric function is considered by the same authors. So, but of course, they don't say non-linear regression, or they still call it as generalized linear models. But I would consider that maybe it is possible in the nonlinear context also, as long as you have differentiable parametric functions with a asymptotic normality available.
okay, sir. Sir, one more question, sir. Suppose if I have a very small sample size, so I mean, in that case, how it will work, sir?
Well, I mean, that is something which, because this theory is always depending on asymptotics. So naturally, small sample size, I would prefer BIC may work slightly better. Because BIC has a built-in posterior theory behind it. So, I mean, like, or similarly, even you have your more parameters, I mean, less number of parameters, BIC works. When you have more number of parameters, oh, by the way, another
sir,
important...
I am using a nonlinear regression. So, I mean, parameter will be selected from the data actually, sir. So, I mean, initially, I am not fixing the, I mean, how many parameters should be there. I mean, I can say, sir, it will be data driven.
But then that needs another approach, because you may have to have because if you are assuming something like a P greater than N kind of a setup, because what I talked today is typically P less than N. Like you have number of parameters which is less than the sample size. But if you are looking at a situation where you have, actually the parameters increase with sample size, something like that, that requires a different kind of an approach, because there was a paper which has come very recently in Scandinavian Journal of Statistics by Klasken and somebody on high dimensional model selection using FIC. So maybe you can 2019 or 2018, I don't remember exactly. So maybe you can have a look at that and then see that, of course, again, they are still in the usual or traditional in the sense, typical regression setup. That paper also doesn't talk about dependent setup. But how far, I mean, maybe non-linearity, you have to see that. I don't remember now the kind of examples that they deal, but you can have a look at that paper. It appeared in the Journal of Scandinavian Journal of Statistics.
Thank you, sir.
Yeah.
Okay. If there is no other questions, let us thank the speaker.
So thank you.
Yeah.
Thank you, Anindya, for.
Yeah. Thank you very much. Yeah, it was a very nice talk.
Thank you, TVR. It was a great talk.
Thank
Good
you.
to see you again.
Thank you.
Nice lecture, Professor Ramanathan.
Thank you, sir. How are you?
Oh, fine. Thank you. Enjoyed your lectures.
Thank you. Thank you very much.
Now we would have just a couple of minutes break before we start the next session. There'll be another talk. Actually, I would be talking in the next lecture, but we may take a couple of minutes break now.
Sure.
Hello. I hope you can hear me. Okay. So let us resume our second session. So here, okay, I would. So I'm self-invited. Okay. So before I start, my talk, I would like to. Yeah. So let me first start. Yeah. So when
Shall I introduce you?
Yeah, of course you may, but yes, I'm just trying hard to start the recording because what I realize is that when I share the screen, then Zoom becomes something it appears only on the top, but hidden thing. Okay, so I'm trying hard to find it out. Yeah. So, yes, so now I think I can, yes, now I can start recording. Yes, Ramanathan, you can of course introduce me.
Yeah,
No
I'll just
problem.
introduce you. Yeah, so friends, good evening. So our next speaker is Professor Anindya Goswami. He is from IISER Pune, and he is very active in the StatFin group. And in fact, he has organized earlier session. Of course, that time it used to be offline sessions, workshops, and we are sort of neighbors. I mean, Pune University is very adjacent to, I would say, IISER. So I'm very happy to introduce Anindya. Anindya has been working in mathematical finance, statistical applications, as well as now I am seeing first time that he is also into data science. So I'm very happy. So maybe I'm the only one who's not getting into that. So, anyway, so welcome Anindya. So the floor is yours.
Yeah, thank you very much. Okay. Okay, so thank you very much. Actually, I am really thankful to StatFin organizers for coming up with this, idea of starting a webinar. And then I was really greedy to actually have my own talk at the first place. Okay, but anyway, so the main purpose of this webinar is to initiate collaborations and exchanging research ideas among ourselves. Ourselves, I mean the researchers who are having similar kind of interest. And so yeah, keeping that in mind, I just would try to give this talk as I mean explainable, and I mean I'll try to demystify all the concepts and the things what is being done in this direction. Okay, and then so let us see, I mean, how much I can do. Yeah. Okay, so this is work basically, due to interest of my students. Okay, so there are a couple of students, Sharan Rajani and Atharva Takshale. So they were very keen in working in something in machine learning, okay, and also in finance. And I remember that, I mean, maybe a couple of years back, before starting this work, I wondered that what can be done, because I always work in mathematical finance, where we assume a model. Okay, we assume a theoretical model, and then we find out theoretical option price, or we find out theoretical best strategy, how to optimize a portfolio. So, I mean, with that type of research expertise, I really was clueless that how can one basically initiate from this type of background a work in machine learning. And of course, the students who were very keen, they were very keen in predicting, okay? predicting stock prices. Okay, so that prediction is something that what math finance, like people like me, who has that training, that due to the market stability, we must assume that there should not be any prediction. Okay, so that return, etc., are uncertain, and let that be that way. So then, it took some time, and then we did some literature survey. We figured out that the option price thing, okay, option price is a deterministic function after all. Okay, from the work of Black-Scholes and hence onward with many other researchers, it is a deterministic function. So there is no predicting here, but that function is unknown due to many different reasons. Okay, so can machine learning capture that unknown function? Okay, so that really attracted my attention. I was really interested in exploring that direction. Okay, so and then while working in that direction, I realized many challenges, many scopes also. So I would try to explain all the challenges and scopes, what I have come across. It is not that I really explored everything in this direction, or it is also not that I am really confident in this direction. However, I would try. Okay, so. Let me give the first motivation. Why should one talk about data-driven approach? Okay, so the fair price of an option contract. So here I'm not, recollecting the definition of option contract. So this is, one financial instrument, which is a derivative instrument whose price depends on price of underlying asset, and not only the price of underlying asset, like present price of underlying asset, but also the trader's anticipation of the future dynamics of the underlying asset. Okay, so that influences price of the derivative. Okay, so this fair price of an option contract, that one can derive theoretically, but that depends on the current anticipation of the future dynamics of the underlying asset. And future dynamics is unknown to everyone. Okay, so the success or failure of theoretical option pricing and hedging is closely tied to the success in capturing the dynamics of the underlying assets price movements. Okay, so that is, in time series, we all know that we have, we can of course have a data, but that data is just one single sample. Okay, just one single sample of the population, and from that, we need to figure out that what should be the distributions and the statistical properties. So, and also that one single sample is also not for the future data. So basically, it is, I think I would not be wrong if I say that working on a situation where you have no data, basically, because we have not taken any data of the future, trajectory. So and the future trajectory depends on some event which are yet to happen, like COVID-19 pandemic or etc. Okay, so, and however, option traders are quoting a price of option whose life is ahead of time, maybe 2 months or 3 months later, and the dynamics of the asset price is going to going to face all the uncertainties in the future. So it is like almost like without any data kind of thing. However, one can believe that, okay, if there is not much market storm, there is not much instability, then past data represents or maybe gives some hints of the future thing. Okay, so that is the kind of scenario for option pricing. So simplified assumptions of theoretical models. Okay, so this is well known that theoretical models have some simplified assumptions, but that do not match the reality. On the other hand, there are, of course, some advancements of theoretical models, okay, with many factor models and with many parameters. So with numerous parameters, it can capture things better, but calibration becomes really challenging. Okay. So since this is a hard problem, adoption of a data-driven approach is in pricing option contracts is gaining attention with the advent of superior computational power. So what happens that in the market, the options are traded. So that is a good news, because since options are traded, so we have some data of input-output kind of thing. And from that, one can perhaps try to capture the relationship. Okay, so that is the idea. So now we recall what is machine learning philosophy. Okay, so it is in very simple term, you have j number of order pairs. So you can call first one as input and second one as output. So imagine these are labeled data set, okay? And here input is coming from a set and output is in a class, okay? So I'm explaining here categorical output. And then from this training data set or given data set, the goal is to find a best mapping, best association function f from xj to yj. Often that is not possible because like deterministic function f from xj to yj, that I mean, for the same xj you may have two different yj's. So that is also possible. So instead of just a single mapping, okay, one would rather say that, okay, from f1, I would find a probability distribution on C, okay, so which would closely be concentrated on yj values, possible values. Okay, so that is the thing. So the algorithm, instead of attempting to find the best possible these things, this function f, that would try to find out the best possible distribution from the domain E to the set of all probability measures on C. And how to do these best things, so that is, some sort of, optimizing some, loss functions, etc. And as in the previous lecture, Professor Ramanathan was mentioning that tail distance, that is really useful, that Kullback-Leibler distance. Okay, so I mean, those type of things, those also have popular name in machine learning literature, that is called cross entropy or something. Cross entropy measure. Okay, so these are the things which are very standard. I mean, this is very broad and general discussion, which applies to almost all supervised learning settings. Okay, it does not matter what algorithm you choose. I mean this type of things do happen there. So the mapping or model is assessed by an objective or loss function. Okay, so in that cross entropy loss function is very popular choice. Of course, there are a few others, but that is also a very popular choice. And these kind of things, how you are going to optimize your loss function, there could be many different algorithms, many different ways it can be done. It depends on the architecture, etc. Okay, so so here, what is the problem here for in the option pricing settings? That we are considering here European call option. Okay, in European call option, we know the price of the derivative at the time of maturity. Okay, as a function of the spot price, the stock price. Okay, if we plot on the vertical axis the option price and the horizontal axis is the stock price, then that appears like this blue line. Okay, so if K is the strike price, okay, of the contract. Okay, so contract price, K is a contract parameter. At the time of maturity, it looks like this. Okay, that is well known. Now, if time to maturity is a little far away, so like 3 months earlier, so time to maturity is 3 months. So then, option prices, one can, without any, model assumption or any mathematical calculations, just by giving economical interpretations, one can argue that, we would be able to get some, a price function profile against is, like this type of convex kind of shapes. But thing is that what are the precise values? Okay, so for precise values, you need a precise model. Okay, unless you know what is the precise distribution of the stock price, one cannot find out these precise values. Okay, but these are deterministic functions after all. Okay, you can always think that this is the unknown deterministic functions, what you would like to understand. And maybe from the past data, you can have some, realization of these values, and from that, a learning algorithm might possibly try to understand these profiles. Okay, so that is the whole, aim for this, problem. Okay, so let me just very quickly talk about the literature in this direction. Okay, so. Just a minute. So I would like to talk about few. I think you can see this, list of papers. I mean, here, okay, yeah, it is now large enough. So I found that this paper by Mallier is apparently is the earliest in 1993. So it is, it is about a neural network model for estimating of prices. So here, 1980 computational resource was also very limited. So here, single perceptron was taken. Okay, so only one thing, one layer kind of thing. Okay, so this is, and almost simultaneously, the work by Hutchinson was also there, Hutchinson, Lowe, and Poggio. So non-parametric approach to pricing and hedging derivative securities via learning networks, okay, in Journal of Finance in 1994. And yeah, so there were some other papers, almost, I mean, immediately after that. Okay, so like 22, you can see that Malieris and Saltenberger's work on. So all these works are for S&P. Okay, so this 23 and 18 was an S&P 500 and S&P 100. So here, the focus was on implied volatility. Okay. And yes, it is also in 1996, around the same time, okay, by Madrala. Okay, so option pricing using artificial neural networks, the case of S&P 500 index call option. Okay, so this is the first paper. Okay, so now, I mean, by saying so, what I'm trying to focus is that the work in this direction is not very new. Okay, so it is, it started quite long. Okay, however, if you look at recent literature in machine learning and an option pricing, not options, in mathematical finance, we don't find too many papers in option pricing. Okay, so we can find more like prediction, because computational power is so good that prediction also is, I mean, there also people are getting some success, okay, with using some machine learning techniques. Okay, so so that is a thing. And then it was, I mean, actually, after I started working in this direction, then I realized that there were earlier works, because when I thought that we can capture this relationship, I did not even know that the work started in 1993 even. Okay, so next, what I have realized is that, so these works, okay, so I mean, mainly when one tries to find an option pricing from a data, then the algorithm becomes only dependent on that particular data. So if that particular model, if you try to use for pricing option of another asset, okay, so that does not work well. I mean, what are the reasons? So that is the question what I was asking, that what is the reason, and trying to understand, because, if you look at the theoretical option pricing, so there, it doesn't matter, correct? That, if you are in the Black-Scholes setting, say, doesn't matter what are the parameters of sigma, etc. The same formula works, correct? And if you are, any other, particular theoretical model, if you consider, and if you change the parameters, etc., so the same formula works. But when you go from one particular asset to another particular asset, what changes? Some parameter changes, correct? I mean, if you have that, the theoretical model in your mind. However, reality is not like that, and real stock price has no obligation to follow any particular model. However, the theoretical option pricing, a fair option pricing, is basically based on the idea that this deterministic function is very particular, okay, and that depends on the dynamics of the asset. So it does not matter what is the symbol of that asset. Okay, various different assets have various different symbols, but so that it depends on the dynamics. So you are going to get different curves, etc. But that relationship should be revealed. Okay. Okay. So so this is the starting. So data looks like this when one looks at option pricing data. Every day there are many different options. Okay, so for a particular day, like here on January 2014, okay, asset price is like 6,301.65, and there are many different assets with different strike prices and different time to maturity. And then with this bunch of data, what data is relevant and how to proceed? So that is the first question. However, what we do is that we filter. The raw data is too much, we filter out. And from the literature also, what we have seen that there is a concept of modularity. That with if one builds a machine learning algorithm which can learn a particular relationship, okay, so there it works well for a particular section of the totality. What is the particular section? That means your options contract, okay, has parameters, strike price, and time to maturity. If you restrict your time to maturity or the strike price in a particular section there, and if you train only those data, so then the model performance increases. And then one can train multiple number of algorithms on non-overlapping sections and then get the predictions and together. So this is like the kind of the modularity concept. So anyway, so what we have investigated, we have taken the near the money, modular that section of the data. So this is number of trained data set. This is number of test data set, and we also believe that predicting or finding out a single option price value is less meaningful. I mean, one can do that. I mean, actually, all the work in the past was like that. So finding out single option price prediction from the algorithm, okay, and then basically it was a regression problem. So, but what we believe that since market is incomplete, so a single price is not a fair price. A fair price is actually a band, okay? So finding out a band is more meaningful. So we tried to find out that a band, okay? So a single predicted price is more confusing. So what we do is that we find a range of fair prices, okay? So we formulate option pricing as a bin classification problem rather than a regression problem, okay? And then there is one more observation, which is basically driven by theoretical understanding of option price, that is called homogeneity hint. Homogeneity hint is something that option price, has some sort of first order dependence on strike price and the option and the stock price. So stock price and strike price, if they are if they are taken ratios, okay, so then if one scale it, like stock price and stock price and option price by the strike price, then one can gain some sort of generality. Okay, so that is one thing, and that was also applied at many different experiments earlier. Like instead of taking stock price as input, stock price divided by strike price, the moneyness was taken as input. Okay, and output as call option price divided by strike price. Okay, of course, input is only not restricted to the stock price, present stock price. Inputs are also includes many other things. Okay, so here we are going to reveal more about it. What are the inputs and what are the outputs? So now, whenever we talk about bins, we need to figure out what should be the bins. So that is a challenging problem. So determining bin width is a really challenging thing. So what we have come up with that error matrix. When we are trying to find out the error between prediction and actual, because I have a training data and test data. So training data was used to train the model, and which can now work on the test data. And from test data, I know actual call option price also, and the model is giving me a prediction price. So these are the bin numbers. And then if we take absolute difference of that and sum over all possible training data, and also multiply the bin width, so then it looks like actually average of the mean absolute error. Okay, so it is just the discretization of the integration. Okay, so then as we understand that if we take W converting to 0, okay, so then it would convert somewhere. Okay, so this converts to that integral. Okay, so given so from that perspective, what we have experimented that by changing bin width, we were observing if the error stabilizes. So of course, if bin width is large, so here it is large, so it is like 1.0 and 0.033. Okay, so it is like the reverse direction. So if bin width is large, then of course the error would be less, and also that would be less useful also, because that had contains less information. So if bin width is smaller, error would increase, but okay, after a certain threshold, since error, EM, the way we have defined, that should converge. So we are looking for the first time here where it was like little stable. That is how we have selected the bin width for this particular data. But now, since we are aiming to see not only it is depending on data, but for various different data also things should work. So we actually took two different data. One is from Nifty 50, another from Bank Nifty. For both the data, we try to find out the same common bin width. Okay, so common bin width that turned out to be 0.1 as a bin width. So this is the 100 times C by K is the number, and that number is on the positive real line. We divide that range in bins. So it appears that maybe 50 different bins are formed. So it is heavily imbalanced class. Okay, and we are really worried that imbalanced class, okay, how the performance, but anyway, we cannot help it because that is the data. So other than this matrix, we also investigated another metric, that is inaccuracy metric, that when this difference is more than 2, and then divided by probability. So that is the kind of thing we also considered. Now the input. So till now I was talking about the output. Now for input, what is very important here is that if the inputs are scale-free in some sense, that means that because one particular asset is moving in the range of 10,000s, another asset is moving in maybe thousands, and then if you train a model using first asset class, of course that trained model would not work for the second asset, because it is in this totally different range, and the model did not learn in that particular region. So some sort of scale-free things. So, but that is standard thing. So these log returns we have taken, okay, and then here one thing what we have realized is that the non-parametric statistics really is really helpful. Okay, so instead of feeding in only the standard deviation, which basically captures volatility, so standard deviation of return which captures only volatility. So what we have done in this approach, we have just taken the order statistics of log returns. Okay, so first order statistics is the feature 1, second is the feature 2, etc. So there are 19 features, so 19 different parameters. Okay, and then of course moneyness, which is stock divided by strike, and time to maturity, and interest rate. So interest rate was obtained from other source. So here 22 features. There's another approach also we have tried. We have checked that instead of order statistics, if we actually incorporate more information, like intraday information, like open, high, low, close. Okay, not only the closing data but OHLC, and there if we also consider the second order moment which appears in the theoretical models of in Black-Scholes, etc. So then I mean, do we get better accuracy? So it also turned out to have 70 number of features. There's another third approach that where we include previous day option price. That means if I'm trying to find out option price of a particular contract, today, I am also going to input the price of the same contract quoted yesterday. Okay, so that we also put here. Okay, so of course this has this extra information, and it turned out that I'm going to show also in a table, that approach and approach 2 are similarly performing. Actually, at some occasions, approach 1 is performing better than approach 2. So that also reveals one fact, that intraday data, open, high, low, close, do not carry extra information of option pricing. On the other hand, that approach 3, their inclusion of the previous day option price, there the accuracy increased significantly. So this is, I mean, if we try to understand what does it mean, I mean, or why should it happen that way? So this actually captures the notion of implied volatility. Okay, yeah. So this is also one occasion I would like to remind. In none of the approaches we actually put in any measure of volatility as input. Okay, so yeah, but because this I mean, what I believe is that if we really want to do a data-driven approach, no statistics which are actually coming from estimation of some parameter which appears in some theoretical model should be included. Okay, so if that is included, so it is like learning that particular theoretical model in a very roundabout way. So no particular measures of historical or linked volatility was input. However, just the information of yesterday's, earlier days option price really helped a lot. Okay, so that is the, that is the learning what we have learned from the experiments. Okay, and now, the participants who are really interested to work in this direction, they may possibly need a little more. So can take a screenshot of this. Okay, so these are hyperparameter values, okay, of XGBoost and ANN, what we have used, the layers, okay. And of, loss function is categorical cross entropy. So this is the experiment setup. So the database NSE, and National Stock Exchange, and then we cleaned etc. data, and we have 3 different approaches, 3 different models we trained so that we can compare. And so the 3 different approaches are giving us 3 different kind of input things. For every approach, we get input from here and output after bin mapping. So we have this input and output. Input lines are, flows are in red color, output are in blue color. So then in training data set has input and output both. So then with that we train the supervised learning. This is standard way of doing this. And for testing data, we just have the input, the red color, okay. And for test data, we just use the input to feed in the model, and in the trained model gives me some output. So that output is the prediction. We can consider, you can call that as a prediction. On the other hand, test data set also has output variable blue, so that we take here and we compare between these two, the prediction and the output of the test data. So for comparison, we have also now 2 different measures. Okay, so like so to check actually, I mean, if one particular measure is giving some sort of preferences, are saying that okay, this particular comparison, like 1, 2, 3, these comparisons, I mean here I mean a particular approach is better than another. So we found it is important to actually consider another type of error, which is completely different, which is rho is basically inaccuracy matrix, which is basically not coming from the ME kind of thing. For category classification error. So so what we have observed that both the matrix resulted in similar type of preferences, similar type of orders, okay, about the approaches. Okay, so that is one learning what we had. And here this is one visualization. So visualizing option price is little hard to do, because however what we have done, for every day from the option price, we calculated the implied volatility. So since our option price is not a single price, is basically a bin or a band basically. So then upper and lower values correspond to upper and lower values of volatilities. So based on that, these gray bands are drawn. On the other hand, actual option price, which have been traded that day, of course, in that day, lots of options have been traded, okay, on that particular asset. But of course, we are talking about modularity. We are talking about only the near ATM options. So in near ATM also there are many options with various different strike prices, but the strike price various different time to maturity. But we have taken a range of time to maturity. There we take the average of that. Okay, so then we get average implied volatility of our data, and then we contrast and we see that some sort of capturing the things pretty well here. So this experiment was done for Nifty 50 data using the approach 3, and in approach 3 also, for every approach there are 2 different supervised models, correct? So here the XGBoost and ANN. So here this is about artificial neural network model. Okay, so So after that, let me talk about another thing, which is, which was also mentioned in the earlier talk by Professor Ramanathan, that when you have two different, way you have models, you can combine those things. Okay, so that is the kind of thing here. This is just one, small experiment what we have just checked, because XGBoost also is giving one particular, supervised trained model, and ANN, from using ANN also we have another trained model, and both are giving some predictions and predicted beans, and we take the average of those two beans. Okay, and then middle point of that, and then when we do that, we get we get some predictions. Okay, and then so we call that ensemble average model. And then we contrast that if we did not have any machine learning algorithm, but we have the data. From the data, we find out what is the historical volatility. And from the value of volatility, we find out what is the Black-Scholes option price. And we contrast Black-Scholes option price against the actual option price. So that contrast would also give me some error. So so for Black-Scholes, so that is the thing what we call for Black-Scholes pricing, we get the error like 0.19. On the other hand, for the model, what we have achieved here. So for that, when we compute the corresponding error in the actual and the model predicted, we get some values like 0.16, etc., which are consistently lower than this value. Okay, so this is done only. This is shown only for Nifty 50, but this has been done for Bank Nifty also. For all the cases, we have seen the same phenomena. For row matrix also, we have similar kind of observation. Okay, but however, this was not our goal. Actually, our goal was not to actually find out a model which works better than Black-Scholes. Our main goal was to understand that what are the challenges of the data-driven option pricing. Okay, of course, you can see that there are some success. Okay, it works a little better than Black-Scholes, but of course, Black-Scholes is not something one should compare with. Because Black-Scholes already has some limitations, everybody knows. Okay, so however, so the challenges and also that performance, when it works well, why should it work well? And when it works, when it does not work well, why does it not work well? So those are the questions what we really wanted to ask and try to explain as much as possible. Okay, so here, in this process, what we have just understood that this combined training is possible under certain circumstances. Okay, so if you train a model, okay, so scale-free input-output we are doing. Okay, so the model can give reasonable predictions when trained on another asset. Okay, provided the log-return distributions are not too different from each other. Okay, so yeah, so although those two assets can have very different price range, but their log return, which is scale-free, okay, if their distributions are not very different from each other, then a very nice thing happens. What happens that here, this is an example where here the model evaluation matrix for model trained on Nifty 50 data. So Nifty 50 data was used to train the models, both the models, ANN and XGBoost. And then with the trained model, we test on the Bank Nifty data. For Bank Nifty also, there are some options, and then we have tested on the Bank Nifty data. And then where there also we have seen that the EM the error matrix are like below 0.19, etc. Okay, which is of course for that also Black-Scholes pricing EM is like this type of values. So here also we are getting that it is performing reasonable. Okay, I mean, at least better than the Black-Scholes option pricing recommendation. So this reveals one thing, that if I am trying to find option price on an asset which is very new and I don't know, that's why I don't have data, still I can use the machine learning algorithm to find the option price, just because that possibly I have trained it using another asset's option price data whose log return was similarly behaving. Okay, so that is nothing unexpected, but okay, so this is good that we have obtained that. And what we have realized is that actually, if the models are trained using McNifty data itself, then the error was actually little larger than these values. Okay. So maybe because that the test and training data time intervals, their Bank Nifty assets dynamics changed, little more. I mean, little towards the Nifty 50 dynamics kind of thing. So or maybe the training data sets, dynamics was little more different than Nifty 50 dynamics kind of things. So that's why, I mean, training on the same day assets data does not help. So what helps is the training with the similar type of log return data. Okay, so this is one small observation. Okay, so combined training. So there we list here the errors. Okay, so and we compare with Black-Scholes pricing errors. So here we see that approach 1 and approach 2, this comparison is very important. So what we are trying to say, so approach 1 does not include open, high, low, close. It just uses close prices, and it uses no statistics like no parametric statistics. It does not use any moments. It's just non-parametric statistics, order statistics, and still it captures similarly or a little better than approach 2. So that is one learning what we have learned from here. And of course, approach 3 gives lowest error. That also teaches us that the past price of the option is really important. Now, another very important question, what everybody would talk about when option pricing comes, that is about arbitrage. Okay, so what is the meaning of arbitrage-free pricing in this context? Okay, so here first we look at this graph. This is the graph what we have obtained by plotting in the horizontal axis the midpoints of the bins. Vertical axis is the closed price from the test data. Okay, so both the prices. Okay, this is so predicted and actual. So then we see that this type of scatter diagram. And then one can draw straight lines. Y is equal to X line, that is the red line, and the green line is the orthogonal regression line. Okay, and then so this is not something unexpected. Of course, if the model is working well, so we should get this type of behavior. It should be middle, but the proximity of red and green line, so that can be taken as a measure of fairness, that whether if there is any bias in the pricing. So that is kind of our recommendation for data-driven option pricing investigation. So we add the identity line, these things, and then the green line also we add that that is orthogonal regression line, and the proximity one can check, one can test hypothesis, one can check the hypothesis that whether slope is really 1 of the regression line and intercept is 0. So this testing gives the confidence of that whether this pricing is unbiased. Okay, so this is one possible way to address the absence of arbitrage, because whenever you created a model and the model is giving a price quoting, the question comes that whether that is going to lead to an arbitrage. So how to ensure that is not, but it is not mathematically tractable. However, one can statistically, address this issue and can with some confidence one can figure out that, okay, so it has arbiter and no arbiter. So this is one methodology what we have recommended. Also, we have observed that the data does not have any fanning effect. It is like narrow, similarly. Okay, so after that, we must also talk about where it fails. It failed badly for during the COVID-19 period data. Okay, so January 2020 to March 2020, so this is the duration we have taken for testing, where this is the COVID period we have considered. Okay, where stock price move, behaved very unpredictably and erratically, and this October to December 2019 as the earlier data section. So if we compare the log return between these two sections, and is this a QQ plot, we see it is far from the diagonal. Okay, so here we can just directly say that it is these two have quite different log return, and I understood that it must be because here during this period the span is much more, huh? So it was much more. And then, of course, so this is during the time from May 2019 to here March 2020, and we are trying to see that where it deviated. So the band is again the predicted band, and the red is the actual implied volatility, the average implied volatility from the actual, and we see that deviation happens here broadly. And we also investigated whether other theoretical models can help here. Okay, so but there in that case we have seen that that is actually even worse than this. I mean, machine learning algorithms could actually did little better than other theoretical models which can be applied here. Okay, so next is that not only this observation, trying to understand why do you observe this way. Okay, so opening the black box. So here what we have done is that we have simulated some test data. Okay, simulated test data with various different volatility. Okay, and for each such test data we found out the error matrix. Okay, obtained from that model. Okay, so now thing is that here you see blue dots and the orange dots. So those are for Nifty 50 and Bank Nifty data. So that means let me correct myself. It's not Bank Nifty data. These are from the models trained by using Nifty 50 and Bank Nifty data. So we have how many models? We have three different models. One is a model trained by Bank Nifty data. Another is a model trained by Nifty 50 data. Another is a model which is trained by both the data, the Bank Nifty and Nifty 50, combined training. Okay. So then what we see that if we take that only single trained data model, and then we test the prediction quality of that model using the simulated GBM with volatility ranging from 1% to 30%, and that is a standard range where it stays. I mean, okay, so 1 is too low. I mean, maybe 8%, 30% was sufficient, but okay, so some range, and we found out corresponding error. What we have observed is that for every single trained model, the error was going high beyond a small interval. And this interval where the error is small, okay, so it's like 0.2, and that means it is below that, so 0.19 or 0.16, etc. So that is near the region what is actually the volatility value of that particular asset. So for example, it is Nifty 50 trained. So if Nifty 50, since Nifty 50 has volatility around 0.14, I mean, why I will say around, because what volatility are you talking about? It could be historical volatility, it could be implied volatility. So these values are a little different, but in the same range of like 0.3, 0.4, etc., 0.13, 0.14, etc., in that range. And in that range, this Nifty 50 trained model was performing well. So that means if I put here GBM with volatility 13% or 14%, and then that trained model predicts more accurately. On the other hand, if I feed in a GBM time series of 30% volatility, then the model trained by Nifty 50 performs very poorly, very poorly. On the other hand, the model which has been trained using Bank Nifty data, that was giving good prediction when my sigma value is like 0.19, 0.22, etc. Mainly because the Bank Nifty has volatility around that value. And now the combined training, what we have done, okay, so that was one small observation in our way, but then we got a very big realization that this combined trained model, that was like we can see it is more wide, and it was giving small values in a wider range. Okay, we see that each blue and orange line, they cross this, so it stays low, so the error stays low. Okay, so that shows one promise that if one actually does combined training, okay, so it is not like we train 5 different models and get 5 different prediction and then average it. No, it is not like that. It is that one single model. Okay, of course, with 5 different prediction and average would give a very good result. Okay, so we are not talking about that. We're talking about one single model, but that is being trained using 5 different assets input. And how can that be meaningful? It is meaningful because if that is done in a scale-free manner, and the approaches what we have listed out, all those are examples of scale-free input. So if scale-free input is followed, then one can get combined training and can one obtain better representation of the space. Okay. Yeah. So yeah, this is a little more details. If anyone is interested to perform similar things, can take a screenshot of this. Okay. So yeah. So I end here. Thank you very much.
Okay, so are there questions?
Anindya, this intervals you got, do you have any interpretation of them as confidence intervals, prediction intervals, some kind of, because you didn't get one value, but you were looking at intervals?
Yes, like option price beans, correct?
Yeah.
So actually, we did not do experiment to find out the interval values in that rigorous manner. Okay, so it was, actually this problem is very tricky, how to find out those ranges. Rather, what we have done is that we have taken a collection of possible ranges, and then we try to figure out which is causing the error matrix table. Okay, so the intervals, the beans, if it is
no,
too large.
I think I'm not talking about that. When you are looking at those fitted values, you have a range. You have these gray things.
Yes, correct. Yes. Yes. So that is correct. Yes. So let me. I think I should reshare again. Yes. Yes. Those ranges are. Yes, you're talking about this. Yes, this is because of the bin. So the bin size, what we have done is that finding out exactly, width of the bin is really tricky. So what we have done, we have taken a range of possible bin widths, like, a fixed bin width. So all the bins are of same width, okay, which is dividing the positive real line. And so for example, starting from 0.1 to 0.033, and then we tried to see that what type of bin width stabilizes the error. We cannot minimize, because of course the error would be least if bin width is too large, but that is not useful. What we can only offer that which stabilizes the error. So this is the plot what we are what we have investigated. So here the error is stabilizes, okay. So then we chose that as the bin width, and when we chose the bin width, we got the bin. Now this is binning of the positive real line, but the algorithm chooses appropriate bin. So chooses appropriate bin from its own supervised learning algorithm, and then in this plot, what you see is that what you see is that those bin, actually it is a little larger than those bin. It is actually twice larger than that bin, basically. So actual implied volatility is not, may not be sometimes inside that the predicted bin, but it could be in the neighboring. Just double the expansion of the bin. So that is the gray region.
So one question.
Did that answer to your question, Ritpurnati?
So these are prediction bands that you obtain for
Correct.
The implied
Exactly.
Okay.
Predict.
Yeah. So my next question is, there are theoretical ways of also obtaining bands for maybe not implied volatility, but option prices themselves, which can be converted to implied volatility. So how do say, for example, the length of these bins, like when we are doing intervals, we are interested not only in the midpoint, but also in the length.
Correct.
How does this method compare to length of bins obtained through some modeling exercise?
Correct, I understand. See, thing is that if this, these lengths here, okay, are of course much larger, because if you see that the implied volatility is fluctuating, so it's like 0.05 here, and here maybe 0.15, like 0.075 kind of length. Okay, so like it is like that means 7.5%, the difference between lower and upper. Okay, so that is very large. So that is for visualization. But actually, if you consider that bin, what we have considered, that bin is basically maybe half of this. So that would be like 3.5% up and down. So that would basically, show that this, that would be narrow. However, sometimes that means a predicted bin does not include the actual value of the implied volatility. Sometimes it includes, sometimes it does not include. Okay, but the question is that so of course that is the thing. But the question what you are asking is that theoretically can one find out any? See, I mean, when we talk about incomplete market, we have some sort of interval where that one can also obtain, in a particular manner. But those intervals are much shorter than this. That should be much shorter than this. However, those theoretical models would not be applicable because there is the model answer, some other uncertainty. So, yeah, because all theoretical models depends on the historical value. So that is the reason we investigated for the Black-Scholes. For Black-Scholes, if we try to see, that is giving even, much larger definition.
Thank you. Okay, so I have one question about
Yes.
that. How you will get that training sample or test sample?
So that is from this, from this, data, this type of data we have. And now, what we have done is that we have taken from the years, I'm trying to find out, yes, 2015 to 2018, 4 years data. And then, first nearly 70% was taken as training data, and later 30% was taken as test data. So that is the kind of way it was done. But exactly percentage was not followed because we really wanted the time. So from a particular, we fixed a particular time. Before that was training, and after that is testing. And Nifty 50 and Bank Nifty, two different assets are there. So the data fraction is little, fluctuating. But that is the, here you can see that it is 10,000 and it is 2,000. So like, understand that that is the.
Yeah, so the thing is, it is on the index only, right?
Yeah.
Okay. Thank you.
Anindya, I just wanted to ask something.
Yeah,
Can I
sure.
ask? Yeah.
Sure.
Yeah. What I was about to ask you was of COVID, but then the next slide was so I mean, I got some answer. It's like, when you compare to British, are you comparing wrong?
Sorry, I could not hear. Could you please again, maybe I will
See,
stop the video.
Yeah. Am I audible now?
Yes.
Okay. So I was actually about to ask you what during the COVID period. But then so I got my.
Oh. That I think he got disconnected. Yeah, again, yeah. Sorry.
There is some problem.
Yes, well, I could understand you're talking about COVID-19 period data, but after that I could not hear anything much.
I was trying to tell you that kind of completely wrong during that period. Here you had this machine learning based things. Is that in fact black holes were not performing at any point of time.
Correct. Yeah.
A comparison, should we compare with something else?
Correct. Yeah. Yes. So exactly. So, but comparing with anything else, like, for example, one can compare with stochastic volatility models, okay, like Houston model, etc. Yeah. So there, of course, one. I mean, we have not done that. We could have done that actually. One thing is that for Houston model, how to calibrate the parameters. That is one tricky thing. Of course, the tricky thing in the sense that consumes lots of computation, because it has 5 different parameters, and then whenever we are comparing, we need to find out the corresponding I mean, because if we try to fit it, what we need to do is that for each and every day, for each and every contract, for last 20 days data, we need to calibrate. We need to calibrate that model,
Right.
And then we need to find out the option price and then do this. So it appeared that it is too much. I mean, it is not that we did not try, but the thing is that it is too much of computation, and yeah, so that is the reason. So basically, I agree with you that one could have tried comparing with some other theoretical model, which could have given better benchmark. So Black-Scholes should never be a benchmark. But since Black-Scholes option price, we could compute very easily because sigma is the only parameter to estimate from historical volatility we have taken, and then we could easily do this. Okay. Also, the main reason is that there are so many experiments we are doing, 3 different approaches. For each approach, there are 2 different algorithms. And also, we are computing 2 different error metrics on that. So then, just for a single run, we had to wait for for a long time. I mean, like very long time, more than a day or something. So to get the full thing. So then changing, and then if more other things if you include, it was almost like very impossible to implement those things. But anyway, one could have done that. Yes. Yeah. Any other question? Yeah. Okay, I think there is no question, and also it is getting late. It is
Anindya, before you close, I will just like to make a few requests and announcements. Firstly, I see a lot of new faces here. That is great. Those of you who have not attended any of the StatFins, can you drop me an email so that I can include you in the mailing list? And from next time, whenever we have these events, I can send you those. So that is one thing. And the other thing is that we are organizing a special issue of Shankha B with on recent advances in statistical finance. So please go to the site of Shankha B and you will see this. The deadline is September 30th for submitting.